So what we're going to do is we're going to take a very easy function, okay, something linear. We've got x plus 2 as our function. And we want to, 1, find the limit of this function as x approaches 3. And then to prove that this limit is the actual value, is the actual limit, the limit that we found, using an epsilon delta technique. So here's what we do. First, to find the limit, we can just get a sketch of this, or we can do direct substitution. So the limit is going to be 5, and I'll leave that to you to determine how you find that limit. But the limit should be equal to 5. We usually call this value L, so we'll usually say that L, or the limiting value, is 5. Now to prove it, this is the hard part, and this is why you're watching the video. To prove it, what we do is we set it up like this. We say, okay, let's let epsilon be greater than 0. Let epsilon be greater than 0 be given to us. Okay. What that means is if I take a look at the function, so let me just see if I can explain this to you on this first one here. So I've got x plus 2. So here's what my graph looks something like this. This is the graph of x plus 2. Okay. And I want to find at 3, if I go up here, okay, I believe that that value, the limiting value, as I go towards the limit, I believe that that's 3. Okay, excuse me, I believe that's 5. So what we're saying is, okay, let's pick an epsilon value. Now we're going to let it be arbitrary. So what I mean is, I'm going to grab an epsilon value, so plus epsilon minus epsilon around the function here, around what I think is the limits. So I think the limits, we're going to call it 5 because that's L. And so what I want to do is I want to prove that that I can find a delta so that all function values are within 5 plus a little bit and 5 minus a little bit. Epsilon being the error amount, how much we're off by. Since we don't know what epsilon will be, it's like a game. Someone picks an epsilon and then you've got to prove that you can find a delta. And they can pick any epsilon they want. So we just say, okay, let's pretend someone picked the epsilon and hid it from us. Okay. Now, regardless of what their epsilon is, as long as it's a positive value, okay, we want to show the following. Okay, so if we let epsilon be greater than or equal to 0 be given, okay, we're going to choose our delta value to be equal to something. Now when I write these proofs, I always leave this piece blank right here, and then later, after I've done some of my side work, I come back and I fill this guy in. So let epsilon be greater than or equal to 0 be given, and we're going to choose a delta, and this is going to be a positive value, and odds are that this number right here is going to be based off of this epsilon. So you're going to see like epsilon plus, or epsilon divided by something, epsilon times something, it'll be in here, okay? If our x values are within that delta, okay, so what we're doing is we're picking a delta down here that's going to be around 3. So positive delta, negative delta. So delta is a value that's positive, and we're floating around the value 3. And if we pick an x value whose distance from 3 is less than that distance delta out to the sides, if that's the case, okay, if any x value that we pick in here is less than delta, okay, then we want the following to hold true. Then we want to show that the function minus the limiting value is less than epsilon. So I need to show that this guy is less than epsilon. That's the proof. So to finish the proof out, I do some side work. Okay, so this is not part of the proof, but it will be. It'll help us. So we're going to get some side work here. So what we do is we start with this guy, f of x minus L, the absolute value of that. So f of x was x plus 2, minus the L value was 5. Now what we're trying to get this guy right here, it looks like a delta there, it doesn't look like a 5. Let's write that a little bit better there. We're going to try to get this guy right here to look like this guy up here. That's what you do in all these proofs. You want to make this look like this. Sometimes it goes very quickly, like in this example, but in other examples you got to play around with it a little bit. And you have to use some like inequalities, maybe like the triangle inequality or whatever whatever the situation calls for. So this is equal to the absolute value of x minus 3 because 2 minus 5 is negative 3. So I've gotten this. Now, we know that this guy is less than delta, but we want this guy to be less than epsilon. So if this guy is equal to this, and this guy is less than delta, if we just let delta be equal to epsilon, then this guy is less than epsilon, because this is equal to this, which is less than this, which is equal to this. So what I've got here in this string, what this implies is that f of x minus L is less than epsilon. So you do this to figure out what your delta value is supposed to be. So we say, okay, delta, let's let delta be epsilon. If that's the case, okay, so if we choose our delta to be equal to the epsilon that the person picked in the beginning, and if we pick an x value that is less than that delta value, okay, from 3, then this is equal to x plus 2 minus 5, which is equal to x minus 3, which that is less than delta, which is equal to epsilon. Therefore, f of x minus L is less than epsilon, which proves that the limits as x approaches 3 of x plus 2, or f of x, that is equal to 5. So because we went through this junk in these two lines right here, we end up getting the proof. And that's how you prove something, limit using epsilon delta. Now this one was a fairly easy one because it was linear with a leading coefficient of 1. We'll try some more that are a little bit more advanced.